Hi, in this video we study the local shape of plane curves. The goal of this video is the determination of the qualitative shape of the trace of a parametrized curve around any of its points. We do this only for plane curves, even though the methodology could be applied to space curves as well. The main tool we are going to use is Taylor's theorem. This important result can be found in any standard course on calculus. We are not going to use it in its full generality, but only adapted to the cases we are interested in. For example, for the third order case, given any differentiable curve defined in an interval and taking values in the plane, and given a fixed value t0 belonging to that interval, we have that the expression of the parametrization can be given according to this formula. That is, the first four terms are a polynomial in t, and the last term is an extra expression such that this limit is satisfied. The interpretation of that last term is as follows. Roughly speaking, this term is much smaller than the rest of the terms for t close enough to t0. This statement, for t close enough to t0, is not quantitative, and that's the reason our study is going to be just qualitative. Hence, for t close to t0, we can have a good approximation of the parametrized curve by just the first four terms. This part is called the Taylor's polynomial, and we are going to use this approximation for our study. In other words, the point of the trace and the first derivatives of the curve at that point give enough information to have a good approximation of the curve. We are going to study this approximation first for regular points, that is, those points for which the first derivative doesn't vanish. After, we'll do also the singular case. In the first case of our study, we assume that the first derivative doesn't vanish, that is, we have a regular point, and that the second derivative is independent with respect to the first one. That is, these two vectors are not proportional. Then, we work with the Taylor approximation just up to order 2. And actually, now we think of the curve t 1/2 of t squared. And we write it in a similar way as a point, the origin, plus t, the vector 1, 0, plus 1/2 t squared of the vector 0, 1. The image has the trace of that curve, which by the way is a parabola, and we also have the point and the two vectors. We compare the last expression on the screen with the approximation we have in the center of the screen. If we do that, following that particular case, we could say that a good approximation of the trace of the curve around that t0 is a kind of parabola, with that point alpha of t0 and those two vectors, the first and the second derivative. These points are called convexity points. The second case, we still assume that the first derivative doesn't vanish, that is, we have a regular point, but now the second derivative is proportional to that first derivative, or even 0, but the third derivative is not. In that case, we consider the Taylor expansion up to order 3, but we can drop the second derivative term because it's proportional to the first one, and t minus t0 squared is much smaller than t minus t0 when t is close to t0. Once we have that approximation, we can think of this other curve, the curve t 1/6 of t cubed, and we write it again as a point plus t, a vector, plus 1/6 t cubed, another vector. The trace of that curve is that cubic, and we also have the point and those two vectors. And we compare this curve with the approximation of the curve in the center of the screen. And then, following that particular case, a good approximation of the trace of the curve around that point will be something like that cubic. We have two images on the screen. The first one, the point and the first and third derivative vectors. On the right-hand side of the screen, we also have that second derivative, which, as we said before, in this case is proportional to the first derivative vector. These points are called inflection points. We now go to the singular case. We assume that the first derivative vanishes. This is a singular point. But the second and the third derivative are two vectors that are independent. That is, they are not proportional. We consider again the approximation of the curve using the third-order Taylor polynomial. We can drop the first derivative, for it vanishes. And now we think of this other curve, the curve 1/2 t squared 1/6 t cubed. And again, we can write it as a point plus 1/2 t squared vector plus 1/6 t cubed, another vector. On the screen, you have an image of the trace of that curve, and we also have the points and the vectors. This is a cusp, and following that particular case, a good approximation of the trace of that curve around the point will be something similar. We have that point and those two vectors, the second and the third derivative. Points like this are called cusp point of the first type. And we have now a good remark. The trace of a smooth curve may have corners, something that perhaps we are not very used to. In the last case we studied, we still assume that the first derivative vanishes, that is, we have a singular point. The second derivative doesn't vanish, but the third derivative is proportional to the second derivative, even 0. And then we have to go up to the fourth derivative to find a vector which is not proportional to the second derivative. We then consider the fourth-order Taylor polynomial of the curve, and we can drop the part associated to the third derivative, as t minus t0 to the cube is much smaller than t minus t0 squared when t is very close to t0. Once we have that approximation, we think of the curve 1/2 t squared 1/24 t to the fourth, and we write it as a point, the origin, plus 1/2 t squared, the vector 1, 0, plus 1/24 t to the fourth, the vector 0, 1. The trace of that curve is a branch of the parabola, going from the top to the origin and then back to the top. With that curve in mind, we can find a good approximation of the trace of the curve around that t0, and will be a kind of two branches of the parabola, from top to the origin and then going back to the top. They are not exactly branches of the parabola, because they are approximation of that curve. Those points are called cusp points of the second type. These four cases give enough information to give a complete result on the qualitative local shape of a curve. In general, let P be the first non-vanishing order of derivation at t0, and let Q greater than P be the first order of derivation at t0 such that the Q derivative and the P derivative are not proportional. Then we have this table of local shapes of curves with respect to the parity of P and Q. We have convexity points, inflection points, cusp points of the first type, and cusp points of the second type. Note that the existence of corners and the change of convexity is related with that change of parity of P and Q respectively.